Howdy, this is a video on section 7.4, Axiom for Negative Numbers. It's based on the Suppess Hill textbook. As we build a simple mathematical system, essentially we're building a group which has an infinite set of numbers, in particular the integers, and it has a binary operation, namely addition. On page 262 of the Suppess Hill textbook, as part of the review test, we're told to state the following axioms in a symbolized form. We have the commutative axiom, the associative axiom, the axiom for zero, and finally the axiom for negative numbers, which, by the way, is what's new, and that's from section 7.4. What's interesting to me, although it's not explicit in the textbook, is that the system we're building is essentially a group. More particularly, it's an Abelian group. And this is a concept that comes from abstract algebra. But this raises the question, what is a group? So a group is essentially a set of elements in some binary operation, such as addition. So right now, when we're completed with this section, essentially we've constructed an Abelian group where we have the so-called integers, and then our binary operation happens to be addition. But what is a group? So the first thing that makes a group what it is closure. And closure just states that if we have the element A, we do some binary operation, star. On B, we get some other output, if you will, C. So A star B is equal to C. The principle of closure just says that A, B, and C must belong to the group G. Those must be elements of that group. So for example, integers are an Abelian group. They do have closure. If I add two integers, you're going to get another integer. You're not going to get something else. So in that sense, integers obey the closure principle. You also have associativity. And here, this is essentially the associative axiom for addition in our case. In other words, for all x, for all y, for all z, in parentheses, x plus y plus z is equal to x plus, in parentheses, y plus z. So a group must uphold this principle. And for integers, once again, this is indeed the case. You also have a so-called identity. So in abstract algebra, it's usually written something like this: E star A is equal to A. So what would E be here? Well, for addition, E would have to equal 0. So the axiom for 0 is really giving us, so to speak, an identity principle. In other words, for all x, x plus 0 is equal to x. And finally, for a group, you have an inverse. And in abstract algebra, this is generally written as A star A to the minus 1 is equal to E. And this is where the axiom for negative numbers comes into play, because we have for all x, x plus a minus x is equal to 0. So E, once again, happens to equal 0. Now the commutative axiom is not essential for a group. However, if you have a group that obeys the commutative axiom, you do have an Abelian group. So the commutative axiom, as you recall, is for all x, for all y, x plus y is equal to y plus x. So this is why we have an Abelian group. And the notion of negative numbers here has allowed us, so to speak, to expand our system to encompass all the integers, and there are infinitely many of them. So just using logic, we have built a very simple mathematical system, and that's kind of interesting. That's kind of cool. As I said, section 7.4 deals with the axiom for negative numbers, and in previous sections we developed other axioms, such as the commutative axiom. We also developed some definitions, namely, we defined a handful of numbers, such as 2, 3, 4, and so on, but that's very limiting. You can't do much mathematics with only a handful of numbers, so it's best to think of a set of infinitely many numbers. For example, the integers. There are infinitely many integers. So, like I said, that set is very small. There's just a small set of numbers. So in this section, we will expand our set to include all integers. There are infinitely many integers. It is an interesting question, by the way, what exactly does it mean to say there are infinitely many members of a set? And can we compare two sets of supposedly infinitely many members? Is there a sense in which one set is bigger than the other, even though both are said to be infinite? That's one of the questions that's raised in set theory and the questions concerning infinity. But in any case, in section 7.2, we developed the associative axiom, and then in 7.3, the zero axiom. Now, there are several number sets that are infinitely large. First off, there's the natural numbers, and these are just the counting numbers, 1, 2, 3, and so on, infinitely, so to speak, to the right. Now, some textbooks count 0 as a natural number, other textbooks do not. Personally, I prefer not to think of 0 as a natural number, but that's just a matter of convention. But we also have the integers. Now, the integers includes the natural numbers, or the counting numbers, but it also includes the number 0 and the negative numbers. And so to speak, we have infinitely many numbers to the right, positively, and infinitely many numbers to the left, negatively. So there's a sense in which we could say that the natural numbers, and there are infinitely many natural numbers, are a subset of the integers. However, do they have the same size? Both have infinitely many numbers, but one is said to be the subset of another one. However, the integers are definitely not a subset of the natural numbers, because, for example, -3, while it's an integer, it's definitely not a natural number. So how could we think about such questions? That's another topic, but it's worth exploring in another video, or go out there and get a book on set theory, because it's a really interesting topic. Now, presently in section 7.4, we will use the algebra property of an inverse to get the negative numbers, that is, x plus minus x is equal to 0. And obviously we can think of an example, such as 7 plus -7 is equal to 0. And so we have our negative axiom for all x, x plus minus x is equal to 0. And now our very simple mathematical system is complete. Example 31, or I should say theorem 31, is on page 258 of the Substance Hill textbook. We want to prove that 1 plus the quantity 2 plus a -1 is equal to 2. It's an obvious statement. We can use our basic arithmetic, but the whole point of this, remember, is to use our axioms and the various rules of inference, and that's it. We want to use our logical toolbox. We don't resort to anything else. Now, to be sure, this is a very nasty proof. I don't like it, but it does give you a sense that we can use logic to build these simple systems. And then in the next slide, we'll look at a much simpler proof. We're going to restate this proof, but in a much simpler way, which is nice. But let's do this. Here's a difficult proof, and all 4 axioms must be used. We will first resort to the so-called logical truth rule. Because the left-hand side and the right-hand side are identical, is a tautology. So that's good to go. It's a true statement. And notice, of course, that we're just stating this left-hand side over here. We're saying it's identical to itself. So that's a good way to begin. But then we're going to do a universal instantiation of the associative axiom, where x is equal to 1, y is equal to 2, and z is equal to a -1. So here, we've just, so to speak, rearranged our groupings a little bit in terms of our parentheses. So here we have this 1 plus 2 grouped together. And then we can resort to the identity rule with lines 1 and 2. So from 1 and 2, we can derive line 3. And notice that we're just saying that this left-hand side is identical with this right-hand side. And we can do that because this and this are identical, because we have this identity relationship really between lines 1 and 2. After all those statements really are just identical to each other, so we can just substitute one for the other. That's the whole point with line 3. And then with line 4, we could instantiate the commutative axiom with x is equal to 1 and y is equal to 2. And this will allow us to do another identity rule inference here with lines 3 and 4. So we can get this. We have 1 plus this quantity, 2 plus or minus 1, is equal to the quantity 2 plus 1 plus or minus 1. So what happened, of course, is this 2 plus 1 here, and this 1 plus 2. So we know that 1 plus 2 is identical to 2 plus 1, so we can substitute this 2 plus 1 in for that 1 plus 2. So that was the point of line 4, of that instantiation of the commutative axiom. So we could then get that to get this inference with the identity rule. And then we can instantiate the associative axiom. X is 2, y is 1, z is minus 1. And then for line 7, we can do another identity rule, this time with 5 and 6. And just a plug and chug kind of game here, and just a shuffling around of parentheses and the like. So that's really what's happening here. But it's very ugly, I admit. And for me personally, see, if I was watching this video right now, the only way I would even get this, because I'm a very tactile, hands-on, and visual learner, I have to write this down and kind of do it. Just looking at this is just a mess, I admit that. So it's best to write it down if you really want to see what's going on, in my opinion. And then for line 8, I did the universal instantiation. The textbook did the universal instantiation of the negative axiom. And here x is equal to 1. And so we can do another identity rule. In a way, we're just substituting one expression for another using lines 7 and 8, because we know, hey, this 1 plus minus 1 is 0, so hey, we can get a 0 in there ultimately. So we get the 0. And then for line 10, we do the universal instantiation of 0 axiom. This time x is equal to 2. And then we do the identity rule with lines 9 and 10, and we can get our desired conclusion. So admittedly, this is just yuck. I don't like this too much. But we can liberalize, so to speak, this proof to make it a little bit simpler. Okay. But even if you don't go into all the bloody details in here and don't work through these problems, because they are nasty or tend to be nasty, to me at least, it shows that logic can construct a simple mathematical system. And that, to me, is of interest. Some of these details here, improving some of these really basic mathematical statements, are just disgusting. But hey, at least in a theoretical level, it's kind of interesting. But we can liberalize this proof at least, and that's what we're going to do in the next slide. To liberalize the proof, we're going to take the identity rule and the logical truth rule and make both implicit, meaning we're not going to have them explicit in our proof. And that's going to cut down on a lot of work. We're not going to have to constantly resort to the identity rule, which makes things much more straightforward and even more simple. Moreover, we can work on just one side of the equation, for example, the right-hand side. So for line 1, instead of using the logical truth rule explicitly, we can do it implicitly and at the same time use our associative axiom. So we're going to do this. We're just going to say that 1 plus the quantity 2 plus or minus 1 is equal to the quantity 1 plus 2 plus or minus 1. And that's just the associative axiom, where x is equal to 1, y is equal to 2, and z is equal to minus 1. And here, the left-hand side is good to go. We have the 1 plus the quantity 2 plus or minus 1. However, we don't have the 2 on the right-hand side. So the right-hand side is what we want to work with. So for line 2, what can we do? We can use the commutative axiom. And the reason we're going to do that is because we're going to want the 1 and the negative 1 side by side ultimately. Because then we can get a 0, and then, hey, we'll have a 2 left over. So that's the whole point right now of using the commutative axiom. So the right-hand side, we can say we have the quantity 2 plus 1, and then the plus minus 1. And that's just the commutative axiom. And here we have x is equal to 1 and y is equal to 1. We have this 1 plus 2. Now we have this 2 plus 1. So we're getting the 1's closer together. Then for line 3, we want our 1's closer together. How can we do that? Well, we have the associative axiom, so we can do a different grouping in terms of our parentheses. So on the right-hand side, we can get 2 plus the quantity 1 plus or minus 1. That's the associative axiom. And x is equal to 2, y is equal to 1, z is equal to minus 1. And here, once again, we don't have to use that identity rule, which is nice. And because the identity rule is nasty and just prolongs everything. So for line 4, we have this 1 plus or minus 1. We do know what that means. Why? Because we have the zero, or not the zero axiom, we have the negative axiom, right? So for the right-hand side, we have 2 plus 0, because we have the negative axiom with x equals 1. So 1 plus or minus 1 is 0. And then for line 5, we can get 2. Why? Because 2 plus 0 is obviously 2. But how do we know that? Well, because of the zero axiom. X equals 2. And there we have it. Just 5 lines. The identity rule is implicit. It's not explicit. And that makes things much more straightforward. It's still tedious, but it's not as tedious. But the point, so you might think, like, how do you even approach such a thing? But note that our goal is a 2 on the right-hand side. We have a 1 and a minus 1. So we have to get those together to get that 0. And that's what we did in our proof. Much simpler. Maybe not so much fun, but at least it's, more straightforward. We will look at one final proof for theorem 36. It's kind of like theorem 31, but that's all right. We have 2 plus the quantity 1 plus or minus 2 is equal to 1. We're going to implicitly assume the logical truth rule. We're going to implicitly assume the identity rule and go from there. The strategy is going to have to be bring the 2 and minus 2 together. So then we can use the zero axiom ultimately to prove what we want to prove. For line 1, we can think about this in terms of the logical truth rule. So the left-hand side is simply 2 plus the quantity 1 plus a minus 2. But right away, we're going to resort to the commutative axiom to modify that right-hand side. And because we want to get the 2 and minus 2 closer together, we'll first resort to the commutative axiom. So we'll say 2 plus the quantity minus 2 plus 1. So that's the commutative axiom. So, and of course, x is equal to 1, y is equal to minus 2. And then for line 2, we're only going to concern ourselves with that right-hand side. We want 1 ultimately. So we'll use the associative axiom, so we can get that 2 and minus 2 close together. So we can say the quantity 2 plus a minus 2, then plus 1 by the associative axiom. And then for line 3, well, we have 2 plus a minus 2. We do have our negative axiom for all x. X plus a minus x is equal to 0. Okay, so we can then say the right-hand side is just 0 plus 1 because we have our negative axiom. Then for 4, well, we can't just say 0 plus 1 is equal to 1 because technically the 0 axiom is x plus 0 is equal to x. Okay, so we'll have to use a commutative axiom before the 0 axiom. So for line 4, we can get 1 plus 0 via the commutative axiom. So that's, it's important to follow what our axiom says. It says x plus 0 is equal to x. It does not say 0 plus x is equal to x. And then finally for line 5, we can finally say the right-hand side is 1 by the 0 axiom. And that concludes that proof. Let's return to abstract algebra. And to do that, we only have to look at exercise 8c from page 261 of the Substance Hill textbook. For example, question 1, what is the identity element for multiplication? So remember that in terms of identity, it has the following property. It just says E star or asterisk A is equal to A. Note that E does not equal Euler's number, by the way. It's just some variable. So for multiplication in this binary operation, what would E have to be? Well, clearly E equals 1 here because 1 times A is equal to A. 7 times 1 is equal to 7, and so on and so forth. And then we could write out the corresponding axiom for all x. 1 times x is equal to x. What about the inverse? So that's another property. So the inverse is just A star A to the minus 1 is equal to E. So for multiplication, what would E be? Well, E we know is 1. And so what would A to the minus 1 be? Well, clearly it would be 1 over x, right? So 7 times 1 over 7 is equal to 1. So A to the minus 1 is equal to 1 over x. And then we could write out the axiom for all x. X times 1 over x is equal to 1. And that does it. We have now completed Chapter 7 of the Substance Hill textbook. Up next is Chapter 8, Universal Generalization. Believe it or not, it only has 2 sections, theorems with variables and theorems with universal quantifiers. I'll cover both sections in the next video, and then we will conclude the Substance Hill textbook. Thank you so much for watching.